In last class, we have seen sampling distribution, central limit theorem, and standard normal distribution. Today, we will see confidence intervals. If you are asked to find the average math score of inter students in Telangana, one option is to collect all inter students math score and take the average, but it will be time consuming and collecting data of all Telangana students will be difficult. Or easier way is we can collect the sample, means some inter students math scores and take the average math scores for that sample. By using this sample mean, we can estimate true average math score of inter students in Telangana. Thus, we can avoid collecting all students' math scores. The sample mean x bar is a point estimate of the population mean mu. If sample is large, x will be good estimate for population mean mu according to the central limit theorem. Because we are using sample mean x bar to estimate the population mean mu, some group of students might have low scores, some group of students might have high scores represented in sample. This is called sampling bias. So it is very difficult to estimate exact value from the sample mean, and we don't know how good that estimation is. If our estimation is in terms of range of values, there will be more chance of success in our estimate. This type of estimation is called interval estimate. Because we are trying to estimate population parameter by using sample, we need to consider sampling error. Margin of error is a statistic expressing amount of random sampling error in study. Means the amount of variability we can expect in results when using samples. Suppose if we repeatedly take samples of size n and calculated those sample means x1 bar, x2 bar and so on, these sample means will be normally distributed with mean x bar. Here we are taking one sample with 3 values and its mean is x1 bar. It is here. If you take another sample which is taken from somewhere here, most of your values are here, then your sample mean will be at this position. Like that, if you select some samples, their sample means will be normally distributed with overall mean x bar. Margin of error describes the distance within which specified percentage of means is expected to vary from this x bar. According to 68, 95, 99.7% rule, we would expect 95% of means, this x1 bar, x2 bar and so on, fall within about 2 standard deviations plus or minus 2 standard deviations either side of this overall mean x bar. But this is a sampling distribution. Its mean will be x bar and its standard deviation sigma x bar is sigma by square root n. So x bar plus or minus 2 sigma by square root n will contain 95% of this sample means. It is a rough estimate. Exactly it is x bar plus or minus 1.96 sigma by square root n. This interval is called confidence interval and the half of the interval is called margin of error corresponding to 95% confidence level, and half of the interval this side or this side, this half part is called margin of error. Generally, at confidence level gamma, a sample of size n from the population having expected standard deviation sigma has margin of error z gamma into sigma by square root n. Here z gamma is the z score, sigma by square root n is the standard error. This margin of error used to calculate the upper limit and lower limit of the confidence intervals, and this margin of error is associated with confidence level. It might be 90%, 95% or 99%. Let's see one example. A machine supposed to fill 250 grams of milk in cup. As machine cannot fill every cup exactly 250 grams of milk, the content added to individual cups so some variation represent that random variation as random variable x. This variation is assumed to be normally distributed around the desired average of 250 grams with standard deviation 2.5 grams. We need to test whether this machine fill the cup with adequate milk. A sample of 25 cups of milk is weighed. The resulting weights are suppose x1, x2 and so on, x25. To guess population mean mu, appropriate estimator is sample mean. Means from sample mean we will infer about the population mean. Suppose if we calculate average value of all these samples, if sample mean x bar is 250.2 grams, if we take another sample of 25 cups, it might be 250.4 or 251.1 grams or any some other different value. A sample with mean 280 grams would be extremely rare. If the mean content of the cup is in fact close to 250 grams. There is a interval around the observed value 250.2 grams of the sample mean within which if the population mean present, then observed data would not be considered as unusual. That range or interval is called confidence interval for population parameter mu. How do we calculate such interval? We can determine the endpoints by using the sample mean x bar. We already know that from central limit theorem, sampling distribution of sample means will follow normal distribution with mean x bar which is close to population mean mu but with standard deviation sigma by square root n. Here sigma by square root n, in our case sigma is 2.5 grams, 2.5 by square root of 25. Here our sample size is 25. So standard error value 0.5 grams. This is the sampling distribution with mean 150.2 grams, which is denoted with x bar. But to find upper and lower bounds easily, we can standardize the sampling distribution by subtracting expected value and then divide with standard deviation of sampling distribution. In this case, it is sigma by square root n. We can standardize by using this formula x bar minus mu by sigma by square root n. Here our standard error is 0.5. In standard normal distribution, we represent random variable x as z. Here random variable is z, if and random variable x here. Now this sampling mean x bar will be 0 in this standard normal distribution. If you want 95% confidence interval, means if machine fills 100 cups, 95 cups content will be within that range, means some lower bound and some upper bound. Within that range of values, 95% of cups content will be there. For example, lower and upper bounds, suppose 245 and 255, 95% of times machine will fill value between these two, 245 and 255. Remaining 5% of times the machine might fill lower than this 245 grams and higher than this 255 grams. Confidence level usually written as 1 minus alpha into 100%. Here alpha is the probability of not observing true population mean in the interval. Means the probability of machine filling these values lower than 245 and greater than 255. We can distribute alpha equally, alpha by 2 on either side of the distribution. Alpha is 0.05 for 95% confidence level. We need to distribute this alpha 0.05 equally in left tail and right tail. Alpha by 2 will be 0.025 and in right side 0.025. We particularly interested in this yellow region. Probability of observing value in this region is 0.95. We want this region's lower bound and upper bound. How can we find this lower bound and upper bound? We can refer Z tables. The entries in this Z table are the area under standard normal curve to Z from minus infinity to up to this Z value. These Z tables contain probability values. These are the probability values. Let's take one example. We have seen this problem. Suppose we have test scores which are normally distributed with mean 55 and standard deviation 10. You pick random score and you want to know the probability, the score below 65. How can we find? You need to integrate this curve from 0 to up to 65 and find the value, that is the probability value getting test score below this 65. We need to calculate the area under this curve up to value x. Here it is 65. Instead that complex integration, we use standard normal distribution table to find the z-score below this 65. We need to represent this value x, which is 65, in standard normal distribution. So we need to standardize this x value by using this formula, x minus mu by sigma. Then it is 65 minus 55 by 10. Result is 1. So this x will be 1 in standard normal distribution and we represent x as z in standard normal distribution. We look up the z table for this 1, then we get the value. See the probability value for z, it is positive 1. So this is the value. See here it is 0.841. It is approximately 0.84. The value 0.841 represents the total probability getting the result less than random sample score 65 with respect to the population. For known z value, we can find the probability by using the z tables. In reverse also possible. If you know the probability value, we can find the respective z score for that probability by using z tables. In our example, we know the total probability up to lower bound, this z alpha by 2, 0.025. In this right tail also probability alpha by 2 equal to 0.025. But we want the cumulative probability up to this point. Total area under this curve is 1. So if you subtract this value from 1, then you will get the cumulative probability at this point z 1 minus alpha by 2, which is the upper bound for 95% confidence interval. If we subtract 0.025 from 1, we will get 0.975, which is the cumulative probability at the upper bound. Since we know the cumulative probability at lower and upper bounds z alpha by 2 and z1 minus alpha by 2, we can find the z scores. Let's see the z scores for z alpha by 2 and z1 minus alpha by 2. You can find the z scores. Let's see the z score for the cumulative probability 0.025. Here value is 0.025. Then see the z score, it is minus 1.9, and for second decimal place it is 0.06. So z score for this cumulative probability 0.025 is minus 1.96. This is the lower bound. And let's see the z score for upper bound. Its cumulative probability is 0.975. See the z score for this probability value. It is here 0.975. Its z score is 1.96. This column and this row. So upper bound z score is 1.96. Between this upper bound and lower bound from minus 1.96 to 1.96, total probability is 0.95. Standard normal variable z, which is x in sampling distribution, it is represented as z in our standard normal distribution, will be within these two boundaries z alpha by 2 and z1 minus alpha by 2 with probability 0.95. So we can replace this z alpha by 2 with minus 1.96 and z 1 minus alpha by 2 with 1.96, and this z with, this is our standardized value, this one, this value, but our parameter of interest is mu, so this will be the lower bound and this will be the upper bound. In other words, lower endpoint of 95% confidence interval is x bar minus 1.96 sigma by square root n, and upper endpoint for 95% confidence interval is x bar plus 1.96 sigma by square root n. Means observing sample mean below this lower bound will be with probability less than 0.025, and observing sample mean above this upper bound will be less than probability 0.025. Means observing sample mean in these two regions is very unlikely. Our parameter of interest mu will be between these two values with 95% confidence level. Let's calculate lower bound and upper bound for our previous problem. Here sample mean is 250.2 and the standard deviation for that sampling distribution is 0.5. Let's substitute these two values in that lower bound and upper bound. Standard deviation is 0.5 and sample mean x bar is 250.2. If you calculate this lower bound and upper bound values, they will be 249.2 and 251.18. So 95% confidence interval is 249.22 to 251.18. Let's summarize. Confidence interval captures a true measure of population using sample data. Confidence interval is a interval value instead of single point estimate. For repeated measurements with same sample sizes taken from same population, x% of times confidence interval calculated for x% confidence level will contain the true parameter value. Confidence interval can be interpreted as confidence interval of 95% does not mean there is a 0.95 probability that the value of parameter mu is in the interval obtained by using the currently computed values of the sample means from this value to this value. Means mu is fixed value. You cannot express it as a probability. Instead, every time measurements are repeated, there will be another value for mean x. This is the sample mean. In 95% of cases, mu will be between endpoints calculated from this mean. Means within these two values range, mu will be there 95% of times. But in 5% of cases, it may not be within this range. See here, if we calculate confidence interval for our previous problem, first time we already calculated. Its mean is 250.2. This sample mean is represented as blue dot, this one, and lower bound it is 249.22 and upper bound 251.8. If we repeat for 20 times, 19 of such calculated confidence intervals contain true mean, that is 250 grams. See here, this red dot is the true mean. All these confidence intervals contain this true mean within their upper and lower bounds. But last one, which does not include population mean, see here, this is the calculated sample mean for some sample and its lower bound is somewhere here and upper bound, but true mean 250, which is outside of this range, means lower than the lower bound. So if you repeat it 100 times, there may be 5 such intervals which might not include this population parameter within this confidence interval range. Width of interval is decided by the margin of error. Wider interval captures population mean accurately, but it is less precise. If you guess the interval from 0 to 500 grams, for our previous problem, that machine has to fill content of 250 grams, but if you guess the confidence interval like 0 to 500, it has wider range. So then if you take some sample, that sample mean will be definitely included within this 0 to 500 grams, but it is less precise. Means you have to guess some confidence interval around some 240 to some 260. That will be more accurate measure instead of this wider interval from 0 to 500. If you increase the confidence level, your margin of error value will be more, so interval will be wider, but your results will be less precise. So instead of increasing confidence level, increase this sample size. It will reduce the width of margin and will give you more precision with more accuracy.